record. That way you don't get the whole Twitch downgraded quality. Okay, so welcome back, everybody. Glad to see you. Well, let's see. How many do we have here? Streamlabs is a little bit slow with updating. I see we have 7 people currently. I'm guessing there's more. Um, so last time, if you missed it, we introed the class. I kind of gave you the heads up of how everything's going to be run. And what we're going to do today is we're going to finish up the introduction slides. Today's kind of my scared straight lecture, so I'm going to tell you all the things that have gone wrong and why software engineering could have been the thing to prevent it from happening. And what we're going to talk about today and Monday, I think I mentioned you're going to also probably see in, I think it's 290. So there is a little bit of overlap, but there's also not a lot of good case studies out there for when software goes wrong. So that's kind of why there's overlap. We're just spending a little bit of time on it, not as much time as you all in that other class. Before we get into that, though, so I originally had the homework assignment. I don't know if anybody noticed it. I put it up at the beginning of class thinking we'd be a little bit further right now. It was due Monday. I moved it to Friday, mainly because the whole purpose of the lab is just to get you up and running, or sorry, the assignment. Kind of the big thing is going to be picking a project team. And what we're going to do on Monday is we'll actually meet on Zoom. So I'll send out an announcement after class with what we're going to be doing. But basically, Monday is going to be let's introduce ourselves to each other since, you've all seen me, but I haven't really seen any of you or heard any of you yet. And I'll try to get you all to form project teams in class. Basically, maybe over the weekend, start thinking about types of projects you're interested in working on. You don't have to have a cohesive idea yet, but if you're interested in making a game, an app, a phone app, a web app, Raspberry Pi or Arduino app, whatever you want to work on, just start thinking in that general direction. And then Monday, maybe we can kind of tease out who is interested in what, and then hopefully teams self-organize. I'll make breakout rooms based on, topics, and then you can all get in there and talk and things like that. So that'll be Monday. Again, I'll send out an announcement with all of that if you didn't quite catch it. The other thing with the homework here is there are articles in the ethics folder. So that's in weekly content under ethics. Basically, so there's the Therac article, which, we're going to talk about Therac as well today. Um, there's the Boeing 737 MAX, which has been in the news. There's the Tesla, which has been in the news quite a bit. I'm just looking for a reflection from you all on who is at fault with the problem, why is it a problem, basically why are they at fault for it, and what should have been done differently. We're going to talk about today, we'll kind of get you thinking about this. But with these software disasters that we've seen, in popular media, they are preventable with proper software engineering techniques, which is the sad thing. Um, so it's kind of good, with a class like this to actually see that software engineering, just software by itself, if you don't do it properly, it can really impact people monetarily, you know, physically in terms of injury or death. If you have a bug on a conveyor belt in a factory and that bug takes that conveyor belt down, every second that that manufacturing facility stops working is like millions of dollars lost. So software development's not as easy as we make it out to be. So I kind of want you all to start kind of thinking real world, I suppose. So that's going to be the plan. Homework, move to next week, Friday is the deadline. And again, just to give you time to form project teams. And I know you probably could have it done by Monday. I forgot to get auto hotkey running again. Sorry about that. Tesla has multiple problems. Excuse me. Couple things with Tesla. I don't have the latest with Tesla. Tesla's falsely labeled autopilot is a marketing problem. It's not autopilot, it's semi-autonomous, so people are not paying attention. Tesla's machine learning algorithms misidentifying, say, the side of white semi-trucks is open sky and people crash into them is another problem. The recent one is hilarious. Let's talk about the most recent one very quickly, and then we'll get into the rest of it. So the most recent one is that all of their screens have been recalled, right? So I think that's every single Tesla. The screen that is your main interface has been recalled. And why is that? It's a hardware and software problem. If you have ever worked on embedded systems like Arduinos or things like that, you know that you have to flash software to it, meaning that you take the code that you write and it gets actually written onto the board. There is a certain number of times that you can write code to a board before it's done. I mean, it's the same thing with solid state drives. It's the same thing with, USB keys. You can only use them a certain amount of times. You will never probably will see that unless you're using them, you know, a lot. Same thing with like micro SD cards. Basically, all of this flash type memory has this issue. You have X 100,000 possible write cycles. Yeah, it's the screen. So basically, what happened was that with all of these software updates that were getting pushed to the screen, you end up going past that write cycle limit, and now you can't update your software anymore. And if you can't update the car, you're screwed. So nobody ever thought to test the upper limit for these write cycles. I still have to look into it more, but it just boggles my mind that something so simple is a massive problem. And again, it's one of these things that we should be catching. But for a car where your entire interface is that screen, that's one of the reasons why I'm kind of freaked out by some of the new technologies we're throwing in cars and things like that. They had that screen on the SpaceX as well. I don't know if anybody watched the SpaceX launches recently, but that whole interface is a touch screen. There's no levers and buttons and dials that I could really see unless they're like hidden. If that screen freezes up, I mean, you are out of luck. Yeah, so if you look up EEPROM, so EEPROM write cycle limits, let's do that really quickly, just for funsies. EEPROM memory has a specified life of 100,000 write/erase cycles. So this is for an Arduino. You can erase it 100,000 times, basically, and then it's dead. So that's the problem. And it's a very, if you've never worked with hardware directly, you probably wouldn't realize that, but you should know that if you're making a system like this. I have no idea how many. I honestly haven't read the articles beyond like the headlines, so I really need to dig into it, but it's just, ugh, come on, guys. Anyway, let's talk about software engineering and some of the other issues we've seen. So this is where we left off last time, right? Software engineering is the process that encapsulates software development. Software development can include hardware because you might be programming devices, right? You might be programming little like Raspberry Pis or Arduinos or things like that. I can have software engineering processes writing this. I used to work in the automotive industry. We had software engineering processes for how we wrote code to the cameras and the radars and the other controllers on the cars, right? You need a process to take a project from inception to conclusion and maintenance successfully. Without one, you're going to have a lot of problems. So a little bit of a dryish slash here's all the things that have gone wrong lecture today, just as a warning. We start thinking about real-ish current style computers in the 40s, right? We have the massive ones. We get to the assembly language, we get through transistors, we start developing operating systems. If any of you are into research, the first conference on software engineering happened in the very late 60s here. Get into 70s, you start talking about things like Unix, big operating systems where multiple people can use them at the same time. What you're seeing here, I'm not trying to like wow you with stuff that you probably already know from like a CS101 class. But if you look at a list like this, you start seeing the complexity increasing over time, right? A simple computer where maybe we're just doing basic math, basic decisions, is a lot simpler than, these quantum computing processors that we're getting into now, right? We're just getting higher and higher in complexity. And how do you manage that is going to be kind of the thing we're talking about here. So we get into our multi-user systems and our databases and all that fun stuff, structured programming, so you're like C, Fortran, COBOLs, that kind of a thing. Then we start adding networking onto it. Let's talk to other computers. Let's allow parallel computing. Let's have an internet where everything is a massive network. Start thinking about object-oriented programming and adding on design patterns. Yeah, I was watching the quantum computing stuff when it came out. It's impressive, and I think you're all going to be the ones that mainly have to deal with with what quantum computing means because it's probably going to be, I would assume, more achievable in your professional lives. But just thinking about like all those encryption algorithms that are completely useless once quantum computing hits, that's all stuff you're all going to have to deal with. So be ready for it. All right, so we have internet. We get into virtual reality. We get into interacting with humans through their voice, video conferencing and streaming and all of this kind of fun stuff. Autonomous vehicles, security, worldwide health record systems. Again, scale and complexity is increasing every decade in computing, and it's probably going to keep increasing, honestly, in complexity, right? Maybe we hit that. Um, it's not Murphy's Law, is it? Is it Murphy's Law? It's the one where basically we run out of transistor space. Something will happen to bring that forward, and things are still going to get more and more complex. And the interesting thing, when we start talking, that'll be semesters of college out the window. Hey, no, it's learning how to learn, right? So if you can pick up the stuff that you're doing now, thank you, Moore's Law. Murphy's Law is the other one that is always appropriate. But what you're picking up now in college, I mean, it's probably newer than what I learned when I was an undergrad, and I'm still able to pick up new things, so I'm sure you'll all be able to pick up quantum when it hits. There's actually like conferences on quantum computing now too, so it's starting to get out there. Anyway, the interesting thing that at least I think when we look at a metric like cost, right? This is a kind of a ham-fisted graph here where it's obviously drawn in PowerPoint or slides with no real metrics, but the cost of software significantly increases over time, whereas the cost of hardware kind of has this logarithmic, let's go down, get cheaper and cheaper the more we manufacture things, right? And come on, come over here. Thank you. The kind of key takeaway here is that with software, we don't necessarily have, this mindset that once we understand something, we can pump it out super cheaply, right? Like with a Raspberry Pi or an Arduino or a real, industrial system on a chip, all the hard work's done at the beginning, and then you can start, except the G. Well, that's a hardware thing though, right? So it's still going to be a lot of initial development, and then once you figure it out, you can mass produce them. Software you can't really mass produce unless you're pumping out like shovelware type things, right? There's a lot of effort that goes into software, and it's basically a new process every time. So why is it hard? Why is it expensive? Isn't software free? You get free updates for life, right? Software is the thing that you give to the computer science nerds and let them work on it, and it's easy, right? No, absolutely not. Software is very hard. Even if it's free and open source, you've still put a lot of time and effort into something, you've released it. You might not be accepting money, but it costs a lot in terms of time and effort. Maybe you have a donation link or something up. So, why is it hard? Every time we write software for a new product, for a new piece of hardware, for something new and shiny, the number of features tends to increase, right? We have to support more things. If you're writing a phone app, you no longer have to worry about your little T9 keyboard. Now you have to handle touch, you have to handle gestures. Maybe you've got, you're using the gimbal on there to check direction. Yeah, we were talking about the NVIDIA last semester too. I feel like we should have figured this out by now. Number of inputs increase, number of outputs increase, and that's more effort that the software developers have to do. Let's say we increase a feature, so we add something to our software. That will exponentially raise the amount of effort that you, the developer, has to go through. All right, so let's look at some of these software applications that are out there. Let's say a trivial project would be something that you would do in your first programming class here. Right? Maybe it takes you a month because, it's hard for you as a new programmer. You're the only person on it, and maybe it's 500 lines of code. So LOC is lines of code here. Fairly trivial, right? Let's do a recursive change calculator or something like that. Not hard in the long stretch of things, but it took you a couple months or a month to do because you're new at it. Then you get into the small projects. Still one programmer. Takes you 4 months though. Say 200,000 or 2,000 lines of code. Still quite small. Complex, but small. Then let's add on a team, right? So now we have 3 programmers. Maybe we've hit 50,000 lines of code. Took us 2 years to write. Let's control a nuclear power plant. Let's control a pacemaker in somebody's heart. It's a small project, but it's complicated. And then let's say that we get into tens of programmers, hundred thousands of lines of code, multiple years, get into Microsoft Word type applications, Windows, compiler optimization. Basically, we start getting into more and more and more complexity with our code base. Right? The bigger the team, the bigger the project, the more code you're going to have to write. And it makes sense. Get into the, I'm going to kind of skip through these. I used Word before. Yeah, because I forgot Word has just become massive in its size. 1 million lines of code. Ultra large scale. Thousands of heterogeneous sensors and units, distributed computing, basically have sensors all over the place. Tons and tons of line of code, many, many programmers, many, many years. Again, I'm not trying to like wow you with, yeah, these things are cool. Here's all of the massive amounts of code that goes into them. Think about the behind the scenes stuff you have to do, right? If I'm writing a massive system that is worldwide, right? Consider the internet, all the servers that have to orchestrate in particular ways just to work. How do you manage that from a engineering perspective, right? How do we test it? How do we make sure that it all works in concert? How do we ensure that you get a good quality of service? These are all kind of the concerns you may have as a software engineer. Let's go back to the pacemaker. How do you make sure that this thing works in somebody's heart? I did hear that, and that's like, that's got to be a gut punch for CD Projekt Red. I don't know why they pushed that out so quickly. Cyberpunk had such a good vibe going for it too. Well, look at the pacemaker though. Let's say that you are a pacemaker manufacturer and you have a device that goes in somebody's heart. What happens if you find a bug after it's been implanted? Does the person go for a software update? Yeah. Yeah, Cyberpunk's a good current example of issues. I feel like that's a marketing and management problem though. Like I think they were forced to put that out. Okay, so the problem with software and why I keep, talking about this, it is difficult to maintain, right? If you put out an open source project on the web and people start using it, you're going to get a bunch of users out there telling you all the things that are wrong with your software, and you may have to maintain it, right? Hey, we found a bug with this particular esoteric system. Please make a fix for it 10 years later. There's always going to be some problem that we find with software. Maybe we didn't catch it with testing. Maybe we didn't catch it in design. Um, there's some edge case that we, the developers, never thought of. It is hard to write software, and it is hard to write good software. Other things too. Let's figure out how long it's going to take us to write software. Let's figure out how much it's going to cost. This is also very difficult to do. So let's say that you're sitting down to scope out your term project and you think, okay, well, I'll work on, every week I'll put X number of hours into it. This week I'm going to work on a main menu. Next week I'm going to work on drawing character sprites. The week after, we'll add in enemies. The week after that, we'll put in artificial intelligence so that they can move around and attack you. And then you start doing it, and then you realize you spent 3 times as long just figuring out what framework to use. It's always tricky to identify how long software dev's going to take and how it's going to cost. Cyberpunk discussion in chat. Love it. It seems like a reasonable game though, right? I mean, it looks pretty. I'm going to go the Bethesda route and wait until the Game of the Year version drops before I pick up Cyberpunk. Hopefully all the bugs have been ironed out by then. But yeah, so we're going to talk about three things. We're not talking about the Denver baggage system that's a little bit out of date at this point, but there's a Ariane missile disaster that happened. Therac people got seriously hurt and or died. We're going to talk about Boeing a little bit too. And basically, we're going to talk about how software engineering could have hopefully prevented some of these things. And again, it's not just people being bad or lazy at their jobs. It could be budget concerns. It could be schedule concerns. Uh, maybe we have to cancel the project. Maybe we push through it. There are a whole slew of things that we can talk about with respect to software engineering. Anyway, case studies. This is where things take a darker turn a little bit. So the first one is the Ariane 5 rocket. Now, this was a rocket that was created by the European Space Agency, or the ESA. 10 years to build, 7 billion US dollars to build it. So this was a massive undertaking. All right. 10 years to build this thing, and they launched it, and 60 seconds later, it exploded. Why did it explode? Somebody was trying to shove a 64-bit number into a 16-bit variable. This is why understanding memory is so important. So here's our rocket. I don't remember the exact part of the code that this was an issue with, but basically what happens when you put a large number into a tiny variable space? You lose a whole bunch of information, right? And if all of your systems are relying on a particular precision of data, you get stuff like this happening. Exactly, yeah. And this happened, the report occurred in the mid 90s here. So this is not at the point where everybody's using like Python or Java and we don't care about memory, right? That's happening behind the scenes. This is at the time when we're still using embedded systems in C and we're writing code that cares about this stuff. Somebody probably just converted. All right, another case study, the Toyota Prius. There have been multiple problems with Toyota devices, but the Prius was that a remote rocket. This one, I don't believe there's anybody on board, at least. So no loss of life there as far as I remember. So the Prius then. One of the things with cars, which you may or may not be aware of, is that all of the safety systems, like your brakes and things of that nature, are becoming computer controlled. So there is software, say, in your brake controller that interacts with your brake pedal, and you're pushing the brake pedal, but you're actually telling the software how quickly to brake, right? It's not just a pure mechanical thing anymore. Now, this brake controller had a delay in it. So I press my brake pedal, and the software has to take time to catch up, meaning that I push the brake pedal and I'm going to go slower than you think you are. Again, as somebody who worked in the automotive industry, anytime we take something away from a mechanical aspect, it just freaks me right out. Yeah. Mainly because I know everything that can go wrong with software. And at least mechanical stuff, you know that it's going to work until it needs to be replaced or maintained. Software can just lock up, right? Anyway, so if you're going at 60 miles an hour, the brakes don't trigger until about 90 feet after your initial brake press. It's a cost savings thing. That's why they're doing it, honestly. It's cheaper to have software than hardware. What happens here too is then there is a disconnect in the ABS system. So that happens when you press the brakes when it's slippery. Now there's a lag there. Oops. And again, I can't remember if there were any issues that happened with people getting hurt or injured, because I'm pretty sure this recall happened pretty swiftly once it was discovered. But just pretend that you're braking on, like Michigan Drive. You're doing 60, 65, even though it's speed limit to 55, and you slam into somebody in front of you because you're pressing your brakes and nothing's happening. Pure software issue here. Yeah, I did show a graph with that. That's exactly right. Software is expensive. Oh, no, I see your point. Um, sorry, it's cheaper to manufacture hardware. It's not cheaper to manufacture software. So once you have that software on there, they think it's cheaper to just roll out updates rather than redevelop hardware over time. Good catch. I like that. Um, One other fun thing to always say that when I was in industry, we had a customer manager promise one of the big three automotive manufacturers free software updates for life. That was a fun time for the team. I think the Chevy Equinox has a lot of problems anyway, doesn't it? Yeah. There's a lot of good case studies with vehicles. A lot of them. All right. Yeah. Well, the thing with the oversight stuff too is it's just amazing what slips through, honestly. All of these things that I've been telling you about here, Toyota has very rigorous software engineering standards, right? This rocket, still made in the 90s, but there was still rigorous testing being done on this thing. Um, I guess one thing I should mention too, which is kind of funny, I went to a conference where they had somebody from NASA giving a talk, um, and he was talking about the Mars landers, so the Mars rovers, that's the Discovery and the other one where they recently died out. They can't do any testing for deploying those spacecraft onto the surface because we don't have anything that you could test. So it's the way he made it sound, like once you launch the satellite up there, once you let the rocket out into space and then you have the lander, it's the first time it's ever been deployed is when it gets shot at the surface of Mars. I guess with that, there's a similar one where I don't have it in the slides here. There's that Mars rover that crashed and died several years back. It's because it was a joint effort. We were using the imperial system and everybody else was using metric, and nobody communicated that. Yeah, oh, that's the thing too. It's always one little thing that causes it. Oh, let's talk about the bad one here, radiation overdosing. This is one that you will be reading about, and you'll hear this over and over again as a massive case study. And the reason why is it's so bad that it bears repeating basically. But the Therac 25, this is a chemo machine, one of those things that tries to get rid of cancer, as you're growing, it's blasting you with radiation. Now, the 25 was an iteration over the 6. So the Therac 6 is one of the radiation machines. It's very common, used quite a lot. The 25 was the upgrade. Bigger number, it's an upgrade, right? Let's do something new here. The difference is it is now completely software controlled. And the thought, and this is in the, I think, late 80s, early 90s when this happened, software is cheap. The graph showed otherwise, but it's cheaper to make software updates than go back and redesign the hardware and redo everything over and over again. So let's get rid of some parts. Software is free to flash. It's not free to manufacture. New thing. The only problem is they took all the safety mechanisms off too. Everything is completely software controlled. In theory, it's cheaper. You don't have extra parts to produce. Other thing too, so this machine, it is a radiation machine blasting you with, radiation. It's going to be extensively tested, right? Let's do as much testing as possible. It took several years to go through this process. Okay, we should be good, right? One problem. One person wrote all the code. So this machine was developed by one person, at least the software. Unit testing and actual testing was minimally done. So it was tested over several years, but that testing was minimal. Interestingly, the developer was one of the testers as well. Other problems here. You can all see where this is going, I'm going to guess. So there were 11 of these installed across North America, so between the US and Canada at least. There were 6 radiation overdoses reported, possibly more, but at least 6 were reported on. Meaning that people are getting blasted with too much radiation, which, as I'm going to guess we all are aware, is a very, very bad thing for the human body. Well, it's probably a small company, right? It's the late 80s. Software companies aren't strictly a thing yet. Yeah, literally one person. Anyway, there were program faults in the prior version. So we have the Therac 6. There was the Therac 20. Didn't show that in the slide, but basically it's like an iteration. So the 6 is completely mechanical. The 20 is mechanical and software based. 25, they take out the hardware and they replace everything with software. And the problem that happened was that there were faults in the 20, but it was never discovered. And why is that? Well, the hardware safety mechanisms were preventing it from ever expressing themselves, right? So we do all this testing on the 20. Hey, all of our tests passed. This is great. We can put it out there. Well, the safety mechanisms were preventing it. These test cases never failed because there was a hardware backup. Once you take those out, those mechanical safety features aren't there to save you. So removing the hardware is a bad thing. And why was this a problem? Well, what occurs in this system are race conditions and concurrency errors. Any of you taken operating systems know what a race condition is? Let's pop this into the chat. What is a race condition? See how long the delay between my stream and the chat is. Two pieces of code executed consecutively. Almost concurrently. It's more of a error. Yeah, so that's a little bit closer. So let's say that you have a variable, right? So let's say int a. You have two pieces of code trying to use it or modify it at the same time. So race condition means that I have 2 bits of code trying to use the same memory space at the same time. And multiple things can happen when that occurs. Everything can shut off. It's like a fail-safe. Or you have no idea what the state of that variable is, right? There's no guarantee on what the output's going to be. With older systems, this wasn't really protected against either. So we have this issue, right? We have a race condition. The humans are also to blame here too. So obviously the programming's bad. Initially, the medical staff didn't believe there was a problem either. They didn't think it was the machine, so they just kept using it. So they're not trained properly. So not only do we have problems with the software, we don't have any safety mechanisms. We also have actually trained people very poorly. Right? So if you see a problem and you don't know what to do, you don't think it's necessarily going to be the machine. The machine's been tested, right? It's safe. Again, software is not just code, it's all the stuff around it, including training your users, which is bad. So basically what happened with these machines is that you have medical staff who are trying to get their job as quickly as possible done, right? So if I have a keypad and probably one of those old terminals where I'm, hitting keys to move around the screen, The nurses and the doctors get used to particular key sequences, so they just hammer them in as quickly as possible. So bip, 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 bip. The machine goes into a race condition state because it can't handle the input quickly enough, and then we get into this overdose state. So let's see, here we go. X to select this particular mode, hit cursor up, hit E to select, hit enter all within 8 seconds. The developers never thought their users would use the keyboard interface that quickly. Oh, people always undervalue hardware. It's boggles my mind. I think I popped a joke into the GVSU Discord about what's the difference between an old programmer and a young programmer. The old programmer still cares about performance. And we don't care about performance anymore when we develop, right? It's all, let's add more RAM or another package that can solve things. Not a jab at any of you, by the way, just I thought it was hilarious. Okay, so we have one person developing things, we have not enough testing, we have training problems. What could we have done to prevent this problem? So a little slide poll for all of you to see if you're thinking about how we could have stopped this from happening. And if you give good answers here, consider it's also one of your homework questions too. So pretty much. Excellent. Testing code review by other developers. This is one thing that we are going to talk about multiple times when we get into the testing areas. If you are a developer and you're by yourself, don't test your own code, right? You overlook things more than one guy. Yeah, absolutely. If it's not broke, don't fix it. True, true. Companies need to iterate though, right? So they need to come up with new products in order to stay relevant. So they probably felt like they needed it. More collaboration and training, absolutely. So great answers popping in here. Rigorous testing team. Don't rush and don't sleep. Don't sleep on the hardware. Oh, that is awesome. Sorry, I've got to where'd my mouse go? Okay. Don't sleep on, I gotta record that one. Thank you. River popped that in, that just made my day. Yeah, if you're a developer, you don't necessarily test all the problem areas, right? You overlook things, whether you want to or not, right? You don't intentionally go in to make bad software, but sometimes you're not the user, so you don't know what they're going to be doing. Exactly. These are all perfect answers. Don't cheap out on development, multiple people, have other people tested, better training, better procedures, everything. These are all great. Yep. Okay. So what does this tell us? This happened a long time ago, relatively a long time ago, and it's still a catastrophe. People got hurt and died from this. The interesting thing with this, and this is one thing to stress, is that the people developing this process, they weren't necessarily incompetent, right? They didn't go out to make a bad product. There was a lot of time and effort spent on these systems. What this does tell us, I don't know, I'm playing with this little twist tie. This tells us that software testing and maintenance is never done, right? You have never tested every single possible condition. You as a developer or as a team, you're never going to consider every single problem, every single use case that is out there. It's just mathematically impossible. I've got to pull up the reference one of these days, but somebody found a bug in the C++ Hello World problem several years ago. Something that's been used forever to teach programming. There's a bug in it. Basically, you're never done maintaining, you're never done testing, is kind of the takeaway here. Now, the Ariane 5 rocket explosion, could we have solved it with a lint test? Lint is static analysis where you check variable types, where you check your coding standards, things like that. Maybe that would have solved it. Could we have done more testing? Always. We can always do more testing, but we still might not catch it. There's a great quote out there involving testing is finding, basically, crap, I'm going to butcher it. So I don't have it in front of me here. Basically, testing is finding the absence of bugs or something of that nature. The kind of the takeaway is there's always a bug in your code. You just haven't found it yet. Testing's not going to tell you that there are no bugs. Testing will tell you that you found the obvious ones. So there should always be a team. Absolutely. Always should be a team. Okay, so software engineering, I'm not going to sell this as the most exciting thing in the world. I will try to make it interesting for you all. It is going to be very dry, I will tell you that, because we're going to be talking about real world issues. We're going to talk about software planning and project management and software processes. And these are the things developers do not want to talk about. But these are the things that structure your code so that you hopefully don't get into these situations. Right? Again, it's easy to go out there and learn how to code, but it's hard to write good code, I suppose. So the things like writing software specs, writing test specs, writing requirements, these are all the things that will constrain your code to something that is achievable and testable. And you might say, well, that's not very exciting. Let's do the fun stuff in here. That's going to be your term project, do the fun stuff in your term project. But keep in mind that when you're writing code, maybe it's a silly little fart app for your phone, and you're not going to hurt anybody with that. But what if you're writing brake controller software? You just, you go to work for an automotive supplier. Say you have an off day and you write some bad code. Well, that could cause somebody to die or to get hurt or to be involved in a massive insurance thing, just to take the automotive example. Your code will directly impact people whether you like it or not. You have to start thinking of this like you're an engineer, not just a programmer. So, kind of the takeaway is to treat this with respect in a way, right? Pretend you're a civil engineer going for a professional engineer's license. The building that you build, if it collapses, people are going to die. If you write bad code, there's a chance you can hurt people. This is not always talked about in programming classes, so just be aware there are real world problems. Now, let's take this a bit further. Let's say you are that person that wrote the software, right? You're going to work for this, medical company. It's going to be great. I get to write software and real world systems and help people. And then we screw up and people are getting radiation burns. One person had a breast amputation. One person died from cancer. How would you feel if you were that person that wrote the code? Again, they didn't do it intentionally. They just followed their process. So one person died on November 3rd, 85 of extremely virulent cancer. This person was overexposed to radiation. That's the kind of thing you're getting into with writing code. And again, I'm not trying to say that this is something you should not do. Just don't be carefree when you're writing code. This is my little soapboxing. All done with that. Just be careful and follow good processes. That's a good quote from Dijkstra. I like that one. Debugging is a process of removing bugs, and programming must be the process of putting that back in. Absolutely. I like that. Okay, so enough dark stuff today. I mentioned on day one that we're going to talk about the practical side of things. We're going to talk about the real world side of things. These are the real world sides of programming, right? Code that you write has an impact on the actual world. We're going to be talking about how software engineering can help us manage that. This entire domain is to make good quality software. So, software engineering. Let's see, I think we're getting close to the end here. Why do we need it? So we're going to protect ourselves, obviously. We're also going to use it to predict how long projects take. We're going to improve quality, maintainability, lower costs, basically build software systems that we could not build without this process, right? Let's create teams. Let's give them processes to follow. You're going to follow Agile. You'll be following Waterfall. Different methods for creating software with all the steps along the way. Now, if you do software engineering poorly or incorrectly, all these goals that you see here are going to be subverted. If you break your process, you're probably going to get crap software, honestly. Your test cases may pass, but they might just be passing to get you past the checkpoint in your process. That's a bad thing. Kind of the key takeaways is that these processes are here to protect us and to make good software. Here we go. Murphy's Law. If anything can go wrong, it will. This is a good one to keep in mind as you move into the working world. Basically, all of these laws, I'll let you read through them on your own leisure. They're kind of nice little... Yeah, there you go. I like Hofstadter's law. It always takes longer than you expect, even when you take into account Hofstadter's law. It's great. Work expands to fill the time available for its completion. Think of any little passion project you've ever worked on and the bloat that you've probably experienced as you think, hey, I could add that cool feature. There you go. So pay attention to these laws. Where are we at 4 slides? Ooh, still have quite a bit left. Yeah, we'll probably, I want to move on to ethics next time, so I'm going to, we should probably talk about this stuff. Maybe what we'll do is we'll start with this next time and we'll go into ethics after that. Yeah, I'm just trying to see if I should keep going or skip over some things. But one thing I want to leave you with basically is that software engineering, we call it engineering for a reason, basically. Think of any engineering discipline you're aware of, like mechanical engineering, civil engineering, electrical engineering, computer engineering. The term engineering means that we understand the science and the theory and the artistry underlying those processes, right? Slides are, yes, they are on Blackboard. They're under weekly content. We're getting to that point with software engineering too, right? So with software. So we got 2 minutes. Let me get through this kind of little fluffy stuff and then we'll end for the day. So when you're developing a new technique, you can think of a craft, right? So you're doing something really beautiful. Maybe you have, a music expert. Maybe you have, an artist where they're creating all these great, great, brand new, beautiful things. Then you turn it into something a little bit more rigorous. So you start off with your woodworkers, your artists. Make something amazing. That's your craft. Then your industry moves to commercial production. Let's take that beautiful thing that you made and let's commercialize it. And not like, selling out to the man commercializing, but let's mass produce these things. What do you need to mass produce? Well, you need to understand how these crafts are put together. You need an understanding of the underlying concepts, right? So the artists, the musicians, they all know music theory. They can pump out, your standard 4-bar songs or whatever. But you're getting into manufacturing. Then you get into engineering, where you understand the theory behind it. You don't just know like how to put things together. You understand the science underneath that. So you go craft to commercializing to engineering. Engineering is where we actually, again, understand the underlying rigor to it. So I'm building some beautiful craftsmanship. I take that and mass produce it. Then maybe I become a civil engineer to understand the structure of this thing that we're building, right? Maybe it's a bridge or a road or a truss or whatever it is. Kind of the key takeaway, though, is that, again, it's an iterative process. Software engineering does the same thing. We start out early on with a craft. We're writing these cool, making these nifty computers and silly little programs, right? We calculate things. Then we move on to, well, we can add some development methodologies onto it. Here are the processes we follow to write code. Then we add in the science. Let's add in algorithms. Let's add in understanding of the underlying logic, underlying, theory of computing, how long something's going to take. Then we move on to the engineering. Here's our software engineering side where we actually have to strengthen our software. We have to ensure quality. We have to make sure that it's never going to fail if we can. Basically, we get to a rigorous viewpoint. So honestly, when you think of software development and software engineering, it is a field of engineering. We should treat it as such. Anyway, I kind of skipped through a little bit there just to kind of get you to the point of thinking, there's computer science and software engineering, what's the difference between these two? It is an engineering process. Anyway, that's going to be it for today. We're at 10:02, so I don't want you all to run, stay late. Any questions from today? Are we all good, hopefully? So homework again, if you missed it at the beginning, push to next week, Friday. All good? Awesome. I'll see you Monday. I will send out an announcement for the Zoom link, and yeah, I will see you then. All right. Have a great weekend. Bye, everybody. See ya.